Have you ever stared up at the night sky and wondered what's really out there beyond the stars we can see? The universe stretches farther than our minds can grasp, and yet scientists tell us we're only perceiving a fraction of it, like standing on the shore of an endless ocean, glimpsing just the surface. But here's the thing that keeps astronomers awake at night. The edges of the cosmos hold secrets that defy everything we think we know. Strange forces, invisible dimensions, even the possibility of other universes lurking just beyond our reach. It's not just empty darkness out there. It's a frontier teeming with mysteries waiting to unravel the very fabric of reality. This video is a journey to those outer limits, where the rules of physics twist into something unrecognizable. We'll explore 30 of the most baffling enigmas that challenge our understanding of space itself, phenomena so bizarre they sound like science fiction. Picture black holes that might be portals to other realms, galaxies moving faster than light should allow, and cosmic structures so vast they shouldn't even exist. Each one of these puzzles is a clue, a piece of a grander puzzle about where the universe ends, or if it even does. What you're about to discover isn't just a list of facts, it's an invitation to rethink everything. Because the more we learn about the edge of the cosmos, the more we realize how much we don't know, and that's where the magic happens. So if you've ever felt that tug of curiosity when you look up at the stars, you're in the right place. By the time we're done, you'll see the night sky and our place in it in a way you never have before. Let's begin. Right now, you might think the universe is everything we can see, every star, every galaxy, spiraling endlessly into the distance. But here's the unsettling truth. Even the most powerful telescopes can only show us a tiny fraction of what's actually out there. This bubble of visibility is called the observable universe, and it's not a physical boundary, it's a limit created by time and the speed of light itself. Imagine the cosmos as a vast, ever-expanding canvas, and the light from distant objects is like paint slowly reaching our eyes. Some of that paint hasn't had enough time to get here yet, meaning entire regions of space remain hidden from view. Now here's where it gets even stranger. Because the universe is roughly 13.8 billion years old, you'd expect the edge of the observable universe to be about 13.8 billion light-years away, the distance light could have traveled since the Big Bang. But due to the expansion of space, that edge is actually much farther, closer to 46 billion light-years in every direction. That means the most distant galaxies we detect are racing away from us so fast that their light is stretched into near invisibility, a ghostly whisper from the dawn of time. Which leads to an even bigger question. What lies beyond that cosmic horizon? Is it just more galaxies, more space, more of the same? Or could there be something entirely different, realms where the laws of physics twist into unrecognizable forms? Some theories suggest that if you traveled far enough, you might find regions where gravity behaves backwards or where time flows in reverse. Others propose that our universe is just one bubble in an infinite cosmic foam, with other universes floating right alongside ours. But the most haunting possibility is this: we may never know for sure, because as the universe expands, those distant galaxies are being pushed farther and farther away, their light fading beyond our reach. Entire civilizations could rise and fall beyond our cosmic horizon, their stories lost to us forever. It's a humbling thought that the universe we see might just be the tiniest corner of something infinitely grander. And yet, every photon that reaches us from that distant edge is a clue, a puzzle piece in the greatest detective story of all time. Even as we ponder the boundaries of the observable universe, there's something far closer, yet equally baffling, tugging at entire galaxies like an invisible puppet master. It's called the Great Attractor, and if you've never heard of it, you're not alone. This colossal gravitational anomaly sits about 250 million light-years away in the direction of the constellations Centaurus and Hydra, pulling thousands of galaxies, including our own Milky Way, toward it at a staggering 1.4 million miles per hour. Think about that for a second. Every star, planet, and speck of dust in our galactic neighborhood is caught in this cosmic river, flowing toward a mystery we can't even see. Here's what makes it so strange. Normally, when astronomers detect massive objects warping space-time, they can at least spot the source, a cluster of galaxies, a supermassive black hole, something. But the Great Attractor, it's hidden behind what's called the zone of avoidance, a thick curtain of dust and stars in our own galaxy's plane that blocks our view. It's like trying to find a lighthouse in a fog so dense, you only know it's there because ships keep drifting toward it. So what could be lurking there? One theory points to an enormous concentration of dark matter, that elusive substance making up most of the universe's mass. If dark matter clumps together in ways we don't yet understand, it could create gravitational pull strong enough to explain the Great Attractor's grip. Others suggest it might be the heart of the Laniakea supercluster, a vast cosmic web where our Milky Way is just one thread among thousands, all drawn toward a central gravitational anchor. But there's a twist. Recent observations hint that the Great Attractor might not be the end of the story. Beyond it, there's something even bigger pulling us, the Shapley Attractor, a megacluster of galaxies over 600 million light-years away. It's as if we've been fixated on a stepping stone when the real cosmic current runs far deeper. What's wildest about all this, these attractions aren't just some distant curiosity, they're actively reshaping our galactic future. Over billions of years, the Milky Way and Andromeda galaxies were already destined to collide. Now, add this unseen force into the mix, and our cosmic neighborhood becomes a high-stakes game of gravitational pinball. And yet, despite all our tech, we're still piecing together the puzzle with half the pieces missing. That's the humbling beauty of the Great Attractor. It reminds us that even in our own celestial backyard, the universe keeps its deepest secrets just out of sight. Just when you thought the Great Attractor was strange enough, the universe throws us an even more perplexing curveball, something called dark flow. Picture this: hundreds of galaxy clusters, each containing thousands of galaxies, all streaming in the same direction like leaves caught in a cosmic wind. This isn't just random motion, it's a coordinated rush toward some unseen destination, as if space itself has a current we can't explain. And here's the kicker: this movement defies everything we know about how the universe should behave. The discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. Scientists noticed that these galaxy clusters weren't just drifting apart due to the expansion of the universe. They were also being tugged in a specific direction, toward a point beyond the edge of our observable cosmos. The speed, an astonishing 2 million miles per hour. That's not just a gentle nudge, it's a full-blown exodus, and no known force in our universe should be capable of orchestrating it. So what's behind this mysterious motion? One theory is as mind-bending as it gets: other universes. Imagine our universe is just one bubble in an endless ocean of multiverses, each with its own physics and dimensions. If a neighboring universe happened to collide with ours long ago, its gravitational pull might still be influencing everything we see, dragging galaxies toward it like a magnet hidden behind a curtain. It's a stretch, sure, but when faced with something this unexplained, even wild ideas deserve consideration. Then there's the possibility of an unimaginably vast structure, something so massive it warps space-time on a scale we've never observed. Think of it like a mountain range so enormous its shadow stretches across continents. If such a thing exists beyond our cosmic horizon, its gravity could be the unseen hand guiding this dark flow. But here's the catch: according to our current understanding of cosmology, structures that big shouldn't exist. The universe simply hasn't had enough time since the Big Bang to form something that colossal. And that's the real puzzle. Dark flow isn't just a curiosity, it's a direct challenge to our models of how the cosmos works. Either we're missing a fundamental piece of physics, or the universe is hiding something far bigger and stranger than we ever imagined. Every time we think we've mapped the limits of what's possible, discoveries like this remind us the edge of the known universe might just be the beginning of the unknown. If the Great Attractor and dark flow feel like cosmic anomalies, wait until you hear about the void of Boötes, a place so empty it defies our understanding of how the universe should look. Imagine a sphere of nothingness stretching 330 million light-years across, a gaping hole in the fabric of space where galaxies should be. To put that in perspective, if our Milky Way were a single grain of sand, this void would be the size of a football stadium, with barely a handful of other grains scattered inside. It's not just space, it's a desert on a scale that feels almost impossible. What makes this void so baffling is the way it upends our expectations. According to the standard model of cosmology, matter in the universe should be distributed somewhat evenly, like froth in a bubble bath, clusters of galaxies connected by delicate filaments with smaller voids in between. But the void of Boötes isn't just a gap. It's a cavern so vast that its existence suggests something fundamental might be missing from our equations. How could such a barren region form? One theory points to an ancient collision between our universe and another bubble in the multiverse, a catastrophic event that might have literally pushed matter out of the way. Others suggest it's the imprint of a supermassive black hole from a previous cosmic cycle, a relic so old it predates time as we know it, the eerie part. This void isn't completely empty. The few galaxies that do linger inside it behave strangely. They're older, redder, and seem oddly disconnected from the rest of the cosmic web. It's almost as if they're survivors of some forgotten era, stranded in a dead zone while the universe expands around them. And here's the kicker, the void of Boötes might not be alone. Astronomers have spotted other megavoid candidates, hinting that these cosmic deserts could be more common than we ever suspected. But the real mystery isn't just their size, it's what they imply about the nature of reality itself. If voids this large exist, did they form by chance, or are they signs of forces we haven't yet discovered? Could dark energy, that mysterious force accelerating the universe's expansion, be sculpting these emptinesses deliberately? Every time we peer into one of these voids, it's like staring into a mirror that reflects back just how much we still don't understand. The universe isn't just full of stars and galaxies, it's also full of absences, and those absences might hold the keys to the biggest secrets of all. The universe is supposed to be uniform, a vast expanse where no direction holds more significance than any other, or so we thought. Then astronomers stumbled upon something so unsettling, they named it the axis of evil. This isn't a cosmic supervillain, but a bizarre pattern etched into the oldest light we can see, the cosmic microwave background. Think of the CMB as a snapshot of the infant universe, a foggy glow left over from the Big Bang. It should look the same in every direction, like static on an old television. But when scientists mapped it in detail, they found hot and cold spots aligned in a way that suggests the cosmos might have a preferred orientation, a cosmic north and south, if you will. What makes this discovery so controversial is what it threatens to unravel. Our entire understanding of the universe is built on the principle of isotropy, the idea that space has no special direction. The Big Bang theory depends on it. If the axis of evil is real, it means the universe might not be as random as we assumed, and that shakes cosmology to its core. Some researchers argue it's just a fluke, a statistical illusion in the data. Others see it as evidence of something far more radical, that our universe is shaped by forces from outside it, like a fingerprint pressed into reality by some unseen hand. One explanation points to the influence of other universes. In certain multiverse theories, collisions between neighboring cosmic bubbles could leave imprints on the CMB, like bruises from a long-ago impact. Another possibility, that the cosmos is rotating, spinning on an axis we can't perceive, stretching space-time itself into a preferred alignment. But here's the kicker, rotation would require a reference point, something outside the universe to define up and down. That's a paradox because by definition, nothing exists beyond the universe unless our entire reality is embedded in something even larger, the wildest part. This isn't just an academic debate. If the axis of evil is real, it could rewrite the rules of physics. Dark energy, inflation, even the nature of time itself might work differently along this cosmic axis. Imagine gravity being slightly stronger in one direction or light bending oddly along a hidden curve in space. It's the kind of revelation that could turn textbooks into kindling overnight. Yet for all its drama, the axis of evil remains unconfirmed. Newer observations have muddied the waters, with some studies supporting the anomaly and others dismissing it as noise. That's the maddening beauty of cosmology. The deeper we look, the more the universe seems to taunt us with glimpses of order, or the illusion of it. Whether it's a flaw in our models or a crack in reality itself, one thing's certain: the cosmos has a way of humbling anyone who thinks they've got it figured out. The Hubble Tension isn't just a scientific disagreement, it's a full-blown cosmic whodunit, one that's forcing us to question whether we've misunderstood the universe's expansion entirely. Here's the puzzle in a nutshell. Two of our most trusted methods for measuring how fast the cosmos is growing keep giving us different answers, and no amount of double-checking seems to resolve the mismatch. On one side, we have the Hubble Space Telescope, peering at pulsating stars and supernova in nearby galaxies to clock the expansion rate at roughly 73 kilometers per second per megaparsec. On the other, the Planck satellite's meticulous study of the cosmic microwave background, the afterglow of the Big Bang, insists it should be closer to 67. That gap might seem small, but in the precise world of cosmology, it's a chasm. Why does this matter? Because the expansion rate, called the Hubble constant, is the yardstick for nearly everything in the universe: the age of stars, the fate of galaxies, even the very fabric of space-time. If our measurements don't agree, it's like trying to build a house with two blueprints that disagree on the length of a meter. One explanation could be simple human error, but after years of reanalysis, both teams stand by their numbers. That leaves us with a far more thrilling possibility. The discrepancy might be pointing to physics we haven't discovered yet. Some theorists suspect dark energy, the mysterious force accelerating the universe's expansion, might not be constant as we've assumed. Imagine it's like a car's gas pedal that's been gradually pressing down harder over time, speeding up the cosmos in ways our models didn't predict. Others propose exotic ideas like early dark energy, a burst of extra push right after the Big Bang that could have subtly altered the universe's trajectory. Then there's the wild card. What if space itself isn't uniform? We've long assumed the cosmos is smooth and evenly distributed. But if we're sitting in a local bubble where matter is sparser than average, our measurements could be skewed without us realizing it. The real kicker: this tension isn't just academic. It could redefine the standard model of cosmology. Every time we think we've got the universe figured out, it throws us a curveball like this, reminding us that the rules we take for granted might be more like guidelines. Whether the solution lies in tweaking Einstein's equations, uncovering new particles, or rewriting cosmic history entirely, one thing's clear: the Hubble tension isn't a problem to solve. It's a doorway, and on the other side could be a whole new understanding of reality. Here's something that might make you look at our galactic neighborhood differently. We could be floating inside one of the universe's biggest empty spaces. It's called the KBC Void, named after the astronomers Keenan, Barger, and Cowie who first pieced together its existence. Picture a bubble roughly 2 billion light-years wide, with galaxies clinging to its edges like dew on a spiderweb, and right near the center. That's us. The Milky Way, along with our local group of galaxies, might be sitting in a cosmic desert far emptier than we ever realized. At first glance, this shouldn't make sense. The universe is supposed to be homogeneous at large scales, meaning matter should spread out fairly evenly. But when astronomers measured the density of galaxies around us, they found fewer neighbors than expected, like living in a town where the closest house is miles away. That anomaly hints at something profound. Either we're in a statistical fluke so rare it's almost unbelievable, or our understanding of cosmic structure needs a serious update. One explanation ties back to dark energy, that mysterious force accelerating the universe's expansion. If dark energy behaves differently in underdense regions like the KBC void, it could stretch space more aggressively here, pushing galaxies outward and leaving us in a growing pocket of nothingness. Another theory suggests this void is a fossil from the early universe, a relic of the slight unevenness present moments after the Big Bang that somehow survived inflation's smoothing effect. But the real kicker, this void might solve one of cosmology's biggest headaches, the Hubble tension. If we're sitting in a low-density bubble, light from distant supernova could be traveling through emptier space than we assume, subtly skewing our measurements of cosmic expansion. It's like trying to judge the speed of sound while standing in a valley. The terrain itself changes the game, yet for all its implications, the KBC void remains controversial. Some argue it's just an illusion caused by observational biases after all. Mapping galaxies is like counting fireflies in fog. Others point to cosmic flows, the meticulous tracking of galaxy motions, which shows streams of galaxies fleeing our local volume as if repelled by its emptiness. Either way, the void forces us to confront an unsettling idea. What if the cosmos isn't just hiding secrets in its farthest reaches, but right here in our own backyard? So next time you gaze at the night sky, remember, those stars might not just be scattered across space. They could be the faint glow of distant shores, while we drift in the quiet heart of a void we're only beginning to understand. And that's the thing about cosmology. Sometimes the biggest mysteries aren't out there at the edge of everything. They're the space we've overlooked all along. Time isn't just a backdrop to the universe, it's woven into its very fabric. So what happens when we reach the edge of reality? Could time itself stop? This isn't science fiction. Some of cosmology's most startling theories suggest that time might not be infinite. Picture a clock winding down until its gears finally freeze. That's the haunting scenario known as heat death, where the universe expands so much that all energy disperses into a thin, cold haze. Stars burn out, black holes evaporate, and particles drift so far apart that interactions become impossible. In this frozen future, there's no change, no events, just an endless, uniform stillness where time loses all meaning. But heat death isn't the only possibility. There's a far more violent alternative, the Big Rip. Imagine dark energy, the force accelerating the universe's expansion, growing stronger over time. Eventually, it could overpower gravity, electromagnetism, even the nuclear forces holding atoms together. Galaxies would tear apart first, then solar systems, then planets, and finally, space-time itself would shatter like glass. In this scenario, time doesn't just stop, it's annihilated in a catastrophic instant, leaving behind a void where not even the concept of before or after exists. Yet some theories offer a twist. What if the end is just a new beginning? Cyclic universe models propose that our cosmos might be trapped in an endless loop. Time could end in a big crunch, a collapse so intense it triggers another Big Bang, or through a cosmic bounce where the universe rebounds like a stretched spring. In these scenarios, time isn't linear but circular, with each cycle erasing the previous one. There's something poetic about that, an infinity of fresh starts, each universe inheriting nothing but the potential for something new. The most mind-bending idea, time might not even be fundamental. Some quantum gravity researchers argue it's an emergent property like temperature, a side effect of deeper, timeless physics. If true, the end of time could just be a phase transition, like ice melting into water. The universe would still exist, but without the arrow of time we rely on to make sense of cause and effect. Here's the paradox: we can't observe the end of time because by definition there'd be no after to witness it. That means these theories will always linger at the edge of science, tantalizingly out of reach. But they force us to confront a profound truth. Time might be the most fragile thing in the cosmos, and if it can end, what does that say about the stories we tell, the histories we build, even the moments we cherish? The universe's greatest mystery might not be where space ends, but when time does. What if our universe isn't the only one? The idea of a multiverse, countless cosmic bubbles floating in an infinite sea of possibility, has long been the stuff of science fiction. But today, it's a serious scientific hypothesis, and the clues might be hiding right at the edges of everything we can see. Picture the universe not as an island, but as a single soap suds in a froth of others, each with its own laws of physics, its own history, even its own version of time. The wild part, if these bubble universes exist, their boundaries could be the most explosive frontiers in reality. Take cosmic inflation, the theory that our universe expanded exponentially in the first fraction of a second after the Big Bang. Some models suggest inflation isn't a one-time event, it's ongoing, constantly birthing new universes in a chain reaction of creation. Imagine a pot of water boiling endlessly, with each steam bubble representing a whole new cosmos. Now, here's where it gets mind-bending. When these bubbles collide, the shockwaves could leave scars on the fabric of space-time itself. Astronomers have even searched the cosmic microwave background, the afterglow of the Big Bang, for strange, circular patterns that might be bruises from long-ago collisions with other universes. But collisions aren't the only way bubble universes might interact. Some theories propose that the space between them isn't empty at all. It's a seething quantum foam where gravity leaks from one universe to another. This could explain bizarre gravitational anomalies, like galaxies moving in ways that defy the pull of visible matter. It's as if invisible strings tether our cosmos to others, tugging at the edges of reality in ways we're only beginning to detect. Then there's the ultimate existential question: what happens at the boundary of our universe? If you could travel far enough, would you hit a wall of pure energy, the membrane separating us from the next bubble? Or would the laws of physics gradually warp, mutating into something unrecognizable as you cross into another realm? Some models suggest these edges might be violent, chaotic places where dimensions fray and particles dissolve. Others imagine them as smooth transitions, like passing through a curtain into another room. The most haunting possibility, we might never know for sure, because if other universes exist beyond our cosmic horizon, their light will never reach us. They could be drifting away forever, their stories forever untold. And yet, every unexplained ripple in gravity, every anomaly in the cosmic background, could be a whisper from beyond the boundary, a hint that we're not alone in the infinite. The multiverse isn't just a theory, it's a mirror forcing us to confront how small our universe might really be. We think we've got a pretty good handle on what the universe is made of until we check the math. Here's the cosmic inventory problem. When astronomers tally up all the ordinary matter, protons, neutrons, electrons, the stuff that makes up stars, planets, and you and me, about half of it is missing. These missing particles are called baryons, and their absence isn't just a bookkeeping error. It's a gaping hole in our understanding of where matter hides. So where do you lose an entire universe's worth of atoms? The answer might lie in the most overlooked corners of space, the vast thread-like webs of gas stretching between galaxies. These aren't just empty voids, they're highways of superheated plasma, so diffuse they're nearly invisible. Picture steam rising from a boiling kettle, but on a scale so immense, a single wisp could swallow 1,000 Milky Ways. This intergalactic medium is so hot, millions of degrees, that it doesn't emit visible light, only faint X-rays. That's why we've missed it for decades, like trying to spot a whisper in a hurricane. But here's the twist. Even with these hidden rivers of gas, the numbers still don't add up, which means the missing baryons could be in an even stranger state, trapped in cosmic filaments as warm hot intergalactic medium, or WHIM. This elusive material is the universe's attic storage, too cool to glow in X-rays, too spread out to block light, but collectively massive enough to tip the cosmic scales. Detecting it requires ingenious tricks like using distant quasars as flashlights. When their light passes through these filaments, certain wavelengths get absorbed, leaving fingerprints of the hidden matter. The hunt gets wilder. Some theorists suggest these baryons might have been flung far beyond galaxies by shockwaves from supernova or black hole jets, scattered like dust in a cosmic wind. Others propose they're hiding in dark galaxies, starless clumps of gas drifting undetected. There's even a fringe idea that some baryons could have decayed into exotic particles, rewriting the rules of what ordinary matter means. The stakes: if we can't find this missing half, it means we fundamentally misunderstand how matter moves and clumps across the cosmos. But with new tools like the James Webb Space Telescope and next-gen X-ray observatories, we're closing in. Every faint absorption line, every flicker in the cosmic background brings us closer to solving one of the universe's quietest but most persistent mysteries. Because in the end, it's not just about finding lost atoms. It's about realizing how much of the universe is still hiding in plain sight. Amid the smooth glow of the cosmic microwave background, one anomaly stands out like a frozen thumbprint: the CMB cold spot. This eerie patch of sky, spanning nearly 1 billion light-years, registers significantly cooler than its surroundings, as if something in the early universe siphoned away its heat. At first glance, it could be written off as a statistical fluke, but the odds of something this extreme appearing by chance, less than 1 in 200. That means we're either staring at a cosmic coincidence so rare it defies belief, or evidence of something far stranger lurking beyond our universe. One explanation points to a phenomenon called a cosmic texture, a theoretical defect in space-time itself. Picture the early universe as molten glass cooling rapidly. As it hardens, tiny cracks might form in its structure. These flaws wouldn't just be empty spaces, they'd be knots of distorted reality where gravity behaves unpredictably. If the cold spot marks where one of these textures unraveled, it could have drained energy from its surroundings, leaving behind a chilling void. The catch: no one's ever observed a cosmic texture directly. Their existence hinges on exotic physics that so far remain purely mathematical. Then there's the more radical idea: the cold spot might be a bruise from a collision with another universe. In certain multiverse models, neighboring cosmic bubbles could occasionally bump against ours, transferring energy in the process. The aftermath: a patch of space left colder than the rest, like a fingerprint on a foggy window. Supporters of this theory note the cold spot's unusual shape, not quite spherical, as if something pressed into the fabric of our universe and left a dent. But skeptics argue it could be simpler: a vast supervoid, an underdense region of space where fewer galaxies mean less gravitational pull, stretching light passing through it and cooling the CMB in that direction. The problem: even the largest known voids can't fully account for the temperature drop. Unless we're missing something fundamental about how these structures interact with light, the math just doesn't add up. Perhaps the most unsettling possibility is that the cold spot isn't an object or an event at all, but a shadow. Some models suggest primordial black holes, born in the chaos of the Big Bang, could cluster in ways that warp background radiation. Others propose it's a flaw in our observations, a trick of perspective where distant structures align to mimic an anomaly. What makes the cold spot so compelling isn't just its mystery, it's what it represents. Every unexplained feature in the cosmic microwave background is like a message in a bottle from the universe's infancy. Whether it's a cosmic defect, a multiverse collision, or something we haven't dreamed up yet, one thing's certain: the cold spot is a reminder that even our most precise maps of the cosmos are still missing whole chapters of the story. And that's what makes it so thrilling, because in the gaps between our understanding, the universe loves to surprise us. The shape of the universe isn't just a geometry puzzle. It's a cosmic detective story with clues hidden in the very fabric of space-time. For centuries, we assumed the cosmos was flat, like an endless sheet of paper stretching in all directions. But modern cosmology has tossed that idea into a whirlwind of possibilities. What if the universe curves gently like the surface of a balloon, or warps outward in a saddle shape where parallel lines eventually diverge? The answer doesn't just define how we map the cosmos, it could reveal whether the universe is infinite or if it has edges we can't yet see. Let's start with the leading contender, a flat universe. This is the simplest model where the rules of Euclidean geometry hold true. Angles in triangles add up to 180 degrees and light travels in straight lines. The strongest evidence comes from the cosmic microwave background, that ancient afterglow of the Big Bang. Tiny fluctuations in its temperature suggest space is flat too, within a razor-thin margin of error. But here's the catch. A perfectly flat universe on observable scales doesn't necessarily mean it's infinite. It could still be wrapped into a finite shape, like a video game screen that loops when you reach the edge. Picture a donut-shaped universe, technically flat, but with boundaries that reconnect. If you traveled far enough in one direction, you'd end up back where you started, like an ant crawling around a giant cosmic pretzel. Then there's the spherical universe hypothesis. Imagine space bending gently inward like the surface of a planet. In this scenario, parallel lines would eventually meet, and the angles of a triangle would exceed 180 degrees. A spherical cosmos would also be finite, a closed loop with no true edges. The kicker: if this were true, the universe's expansion would someday reverse, collapsing back into a big crunch. But observations of dark energies accelerating push make this outcome seem unlikely, leaving the spherical model on shaky ground. Now the wild card, a saddle-shaped universe known in math terms as hyperbolic geometry. Here, space curves outward in multiple directions, creating a surface where parallel lines perpetually diverge. It's the geometric equivalent of a Pringle chip, a shape that seems impossible to visualize at cosmic scales. Yet some theories of quantum gravity suggest this could be reality, with space-time crumpled by the violent energies of the early universe, the real twist. Topology, the study of shapes and their properties, might hold the key to hidden boundaries. Even if the universe appears flat, its global structure could be folded in ways we can't directly observe. For instance, if space is shaped like a dodecahedron, a 12-sided die, light could wrap around it, creating ghostly duplicates of distant galaxies. Astronomers have searched for these mirror images in the cosmic microwave background, but so far, no luck. What's at stake isn't just academic. If the universe has a finite shape, it means there's an edge out there somewhere, a place where the rules we know break down. Could boundaries be veiled by cosmic horizons or guarded by forces we've yet to discover? Or is the cosmos truly infinite, an endless expanse where every possibility repeats endlessly? The shape of the universe isn't just about geometry, it's about the very nature of existence. And until we crack this mystery, we're like flatlanders trying to comprehend a 3D world, unaware of the dimensions lurking just beyond our grasp. We often picture the Big Bang as an explosion, a single point erupting outward into space. But here's the twist: it didn't happen somewhere, it happened everywhere. The Big Bang wasn't an event in space, it was the birth of space itself. So when we ask, where's the edge of the Big Bang, we're grappling with a paradox. If the universe has no center, how could its origin have a location? Yet, there's a tantalizing possibility that the furthest reaches of the cosmos might still hold echoes of that primordial moment, like shadows cast by the first light. Think of it like standing in a vast, foggy field. As the fog clears, you see more of the landscape, but no matter where you stand, the horizon always looks the same. That's our universe. Every direction we look, we see galaxies receding, their light stretched into red hues by the expansion of space. But if we could peer far enough, we'd hit a wall of sorts, the cosmic microwave background, the afterglow of the Big Bang's fiery infancy. This faint glow isn't just radiation, it's a snapshot of the universe when it was just 380,000 years old, a time before stars or galaxies even existed. Now here's where it gets surreal. Some cosmologists suggest that if the universe is finite but unbounded like the surface of a balloon, the CMB might contain repeats patterns that loop like a broken record, hinting at a cosmos smaller than it appears. Others hunt for anomalies in the CMB that could mark where our universe's structure brushes against something else. Imagine a bubble universe expanding into a froth of others. Its edges might bear wrinkles from collisions long ago. But the real enigma lies in quantum fluctuations. The seeds of today's galaxies were sown by microscopic ripples in the Big Bang's energy field. If those fluctuations weren't perfectly random, if they skewed in certain directions, it could mean the universe has a hidden asymmetry, a fingerprint of its birth. Some theories even propose that the Big Bang's remnants might include cosmic strings, flaws in space-time thinner than an atom but stretching across the observable universe, vibrating like guitar strings plucked by creation itself. So is there an edge to the Big Bang, not in the way we'd expect, but the universe's furthest horizons might still whisper secrets about how it all began not as a place, but as a transformation of reality itself. And that's the beauty of this mystery. The farther we look, the closer we get to the moment when everything was the edge. Imagine pouring gasoline on a fire, expecting the flames to slow down, only to watch them explode faster instead. That's exactly what dark energy is doing to our universe. This mysterious force isn't just pushing galaxies apart. It's making them flee from each other at an ever-increasing rate, as if space itself has a hidden throttle stuck in overdrive. What makes this so unsettling is that according to everything we know about gravity, the expansion should be slowing down. Matter attracts matter, so the collective pull of galaxies ought to be putting the cosmic brakes on. Instead, something we can't see or touch is overpowering the entire universe, stretching it toward an unknown fate. The story starts in the late 1990s when astronomers studying distant supernova made a jaw-dropping discovery. These dying stars were dimmer than expected, meaning they were farther away than our models predicted. The only explanation, the universe's expansion wasn't just continuing, it was accelerating. The culprit earned the name dark energy, not because it's sinister, but because it's utterly invisible, detectable only by its gravitational repulsion. Today, we think dark energy makes up a staggering 68% of the cosmos. To put that in perspective, everything we can see, stars, planets, nebulae, accounts for less than 5%. The rest, that's dark matter, another enigma. But dark energy, it's the dominant player in the cosmic game, and we have no idea what it actually is. One leading theory ties dark energy to Einstein's old nemesis, the cosmological constant. Back in 1917, he introduced this fudge factor into his equations to keep the universe static, calling it his greatest blunder when expansion was later discovered. But what if he was accidentally right? The cosmological constant could represent the energy of empty space itself, a property of the quantum vacuum where particles flicker in and out of existence. The problem, when physicists calculate how much energy this vacuum should have, the number is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's the worst mismatch in science, suggesting we're missing something monumental. Then there's the phantom energy scenario, a nightmare version of dark energy where its strength grows over time. Picture this force not just pushing galaxies apart, but eventually ripping apart solar systems, planets, even atoms. This big rip could unravel the fabric of reality in a cosmic apocalypse where space-time itself tears at the seams. The timeline, some models suggest it could happen in as little as 22 billion years. On the cosmic scale, that's practically tomorrow, but dark energy might not be constant at all. Alternative theories propose it's a dynamic field, like an invisible fluid permeating space with properties that evolve. Some models even suggest it could decay, flipping from repulsion to attraction and collapsing the universe in a catastrophic reversal. Others whisper about a connection to extra dimensions, leakage from hidden realms warping our perception of cosmic expansion. The real puzzle, dark energy, might not be one thing but many. Just as dark matter could consist of multiple particle types, dark energy could be a cocktail of exotic phenomena we've yet to imagine. Every unexplained motion of galaxies, every anomaly in the cosmic web might be a clue to its true nature. And here's the kicker: because dark energy operates on intergalactic scales, we're like ants trying to study an ocean by watching a single drop. Our entire observable universe might just be a speck in a much larger tapestry where dark energy behaves completely differently. What keeps scientists up at night isn't just the mystery, it's the realization that dark energy isn't just shaping the universe's future, it's rewriting the rules of reality as we go. And until we crack its code, we're sailing into the cosmic unknown with a map that's missing its most important landmark. Deep in the constellation Eridanus lies one of the universe's most perplexing absences, a void so vast it could swallow thousands of Milky Ways without a trace. This is the Eridanus supervoid, a cosmic emptiness stretching over 1.8 billion light-years, a place where galaxies are conspicuously scarce. But this isn't just another gap in the cosmic web. What makes this void extraordinary is its eerie alignment with the CMB cold spot, that mysterious cold patch in the afterglow of the Big Bang. Are these two anomalies connected, and if so, could they be rewriting the rules of cosmology? For decades, astronomers assumed the cold spot was a cosmic illusion, a trick of statistics. But when the Eridanus supervoid was discovered lurking in the same direction, the coincidence became too striking to ignore. Here's why: when light travels through a void, it loses energy climbing out of the gravitational well, a phenomenon called the integrated Sachs-Wolf effect. The result, light arriving from beyond the void, should appear slightly cooler, like a traveler exhausted after crossing a desert. The problem: the Eridanus supervoid, as massive as it is, shouldn't be nearly big enough to explain the cold spot's extreme chill. The temperature drop is about 70 microkelvins, far more than this void alone could account for. This mismatch has sparked a firestorm of debate. One camp argues we're seeing a rare but natural fluctuation, a chance alignment of smaller voids amplifying the effect. Others propose something far more radical, that the supervoid is a scar from an ancient collision with another universe. In this scenario, the energy drained by the collision left behind not just a cold spot, but a sprawling emptiness where matter was violently pushed aside. It's like finding a crater where the impactor isn't just missing, it's from another dimension entirely. Then there's the quantum possibility. Some theorists suggest the supervoid could be a remnant of a phase transition in the early universe, a moment when space itself cracked like ice under stress, leaving behind pockets of abnormal density. If true, the Eridanus supervoid isn't just a hole. It's a fossil, a snapshot of the universe's chaotic infancy frozen in time, yet the boldest idea of all. That the void isn't empty at all. What if it's filled with an exotic form of dark energy, one that repels matter more aggressively than we've ever observed? This could explain both the cold spot and the void's unnatural sparseness. Imagine a hidden force lurking in that darkness, sculpting the cosmos in ways we're only beginning to glimpse. But here's the twist. The latest surveys suggest the supervoid might not be as underdense as we thought. Some regions within it contain faint, diffuse galaxies, hinting that the void could be a patchwork of smaller empties rather than a single gaping chasm. That's reignited the statistical fluke argument, but even if chance is at play, the odds of such a perfect alignment with the cold spot remain astronomically low. What's at stake isn't just one mystery, it's the integrity of our cosmic models. If the Eridanus supervoid and the cold spot are truly linked, they could expose flaws in our understanding of gravity, dark energy, or even the Big Bang itself. Or they might be a cosmic mirage, a reminder that sometimes the universe's greatest tricks are played on the ones trying hardest to see. Either way, this void isn't just an absence. It's a question, one that echoes across billions of light years, waiting for an answer. We like to think the universe has a single, definitive age, but what if our measurements are telling us conflicting stories? The cosmos is currently pegged at roughly 13.8 billion years old, a number derived from the cosmic microwave background and the expansion rate of space. Yet when we look at some of the oldest stars in our galaxy, like Methuselah, their estimated ages flirt dangerously close to that limit, even slightly exceeding it in some calculations. How can stars exist that seem older than the universe itself? This paradox isn't just a glitch in the math. It might be a clue that the edges of reality are warping our perception of time. Take the Hubble constant, the speed at which the universe expands. Measurements based on nearby supernova suggest a faster rate than those from the CMB, leading to a younger universe in one dataset and an older one in another. This tension suggests something fundamental is missing from our models. One possibility: the influence of vast cosmic structures near the universe's edge, like the KBC void or the Great Attractor, could be subtly distorting the path of light in ways we haven't accounted for. Imagine trying to clock the speed of a car while standing on a moving walkway. If the ground beneath you is also shifting, your readings will be off. Then there's dark energy's role. If its strength has varied over time, early expansion could have been slower or faster than we've assumed, throwing off our cosmic clocks. Some theories even suggest time itself flowed differently in the universe's infancy due to extreme densities, meaning a year near the Big Bang might not equate to a year today. It's like comparing a sundial to an atomic clock. Both measure time, but under wildly different rules. The most radical solution: the universe might not have a single age at all. In a multiverse scenario, our cosmos could be a bubble in a much older foam, with time behaving differently beyond our horizon. Or gravitational time dilation near supermassive black holes at the edge of observable space might create pockets where the local age differs drastically from the cosmic average. What's clear is this: the universe's age isn't just a number. It's a puzzle, one that forces us to question whether we're reading the cosmic clock correctly, or if the hands themselves are being twisted by forces we can't yet see. Every discrepancy isn't an error, it's an invitation to look deeper. What if we're living in a cosmic illusion, a pocket of space so sparse that it warps our entire view of the universe? This is the phantom void hypothesis, a mind-bending idea suggesting our galaxy floats inside a vast bubble of near-nothingness, skewing everything we measure beyond it. Think of it like standing in a valley at dawn, watching sunlight hit distant mountaintops first. From your low vantage point, you'd swear the sun rises earlier for them, but it's just an artifact of perspective. Now scale that up to galactic proportions. If we're nestled in a void billions of light years wide, its gravitational quirks could be bending our cosmic yardsticks without us realizing it. The math behind this is as elegant as it is unsettling. Normally, astronomers assume the universe's matter is distributed fairly evenly. What you see in one patch should roughly match another. But if our local neighborhood happens to be unusually empty, the implications ripple outward. Light passing through this underdense region would gain energy as it enters, since there's less gravity pulling it back, and lose energy climbing out, subtly shifting the apparent brightness and redshift of distant supernova. These are the same measurements we use to calculate cosmic expansion, meaning a void could trick us into thinking dark energy is stronger than it really is. Here's where it gets controversial. Some studies suggest the KBC void, a proposed low-density region about 2 billion light-years across, could explain the infamous Hubble tension, that nagging mismatch in expansion rates. If we're inside this bubble, nearby galaxies would appear to recede faster simply because space is emptier here, while the outer universe's expansion rate would seem slower by comparison. It's a cosmic sleight of hand. The discrepancy might not be about dark energy's behavior, but about our unlucky seating arrangement in the grand theater of space-time. But not everyone buys the phantom void idea. Critics point out that such a massive underdensity should leave glaring imprints on the cosmic microwave background, distortions we haven't clearly observed. Others argue that galaxy surveys show filaments and walls threading through our local volume, making it far from empty. Yet proponents counter that voids aren't perfect vacuums. They're sponge-like with hidden pockets of matter, and their subtle gravitational lensing effects might still lurk beneath detection thresholds. The most tantalizing twist, if this hypothesis holds, it would mean we've misunderstood dark energy's role entirely. Rather than a mysterious force rampaging through the cosmos, its apparent acceleration could just be a mirage, a side effect of our lonely corner of existence. That wouldn't just solve one puzzle, it would rewrite the cosmological playbook, turning our grand narrative of universal expansion into something far more nuanced. Of course, the phantom void remains unproven, but that's the beauty of frontier science. Sometimes the most radical ideas force us to ask better questions. Whether this hypothesis lives or dies, it's a reminder that the universe doesn't just hide its secrets in distant galaxies or exotic particles. They might be hiding in plain sight, woven into the very emptiness around us. At the heart of every black hole lies a paradox so profound, it threatens to unravel our understanding of reality itself. The black hole information paradox isn't just about gravitational monsters devouring matter. It's a cosmic crisis where quantum mechanics and general relativity collide, and the stakes couldn't be higher. According to quantum theory, information, whether it's the spin of an electron or the pages of a book, can never truly be destroyed. Yet black holes, by their very nature, seem to erase it completely. So where does that information go? And if it's trapped behind an event horizon, could the universe's edges hold the key to its escape? Let's break this down. Imagine tossing a chair into a black hole. Under classical physics, that chair and all the information about its shape, material, and structure would be crushed into oblivion at the singularity. But quantum mechanics insists the information isn't gone, it's just scrambled. The problem: if the information remains inside the black hole, it's effectively lost to our universe forever once the black hole evaporates via Hawking radiation, a slow leak of particles that eventually causes the black hole to vanish. That's like burning a book and claiming its words still exist in the smoke, even as the ashes dissolve into nothingness. This paradox led Stephen Hawking and others to propose radical solutions. One idea suggests information isn't trapped inside the black hole but encoded on its event horizon, the point of no return. Think of it like a hologram where a 3D object's data is stored on a 2D surface. If true, every particle swallowed might leave a faint imprint on the horizon, a cosmic fingerprint that persists even as the black hole fades. But here's the twist: if information lingers there, could it somehow propagate to the universe's edges? Could the event horizon be a gateway, not just a prison wall? The plot thickens when we consider black holes as cosmic recyclers. Some theories posit that what goes into a black hole doesn't stay there. It's ejected through white holes or wormholes, emerging elsewhere in space-time. In this scenario, information might not be lost but rerouted, popping up in distant corners of the cosmos, perhaps even beyond our observable universe. Picture a library where books aren't burned but teleported to another branch light years away. The catch: we'd never know because that other branch could lie outside our cosmic horizon, forever out of reach. Then there's the firewall hypothesis, a nightmarish twist where the event horizon isn't smooth but a raging wall of energy that obliterates anything crossing it. If correct, information isn't so much lost as annihilated in a quantum inferno, violating the very laws we're trying to preserve. This idea is so controversial it split the physics community, with some calling it a reductio ad absurdum, a sign our theories are missing something fundamental. The boldest answer: black holes might not be the end of information but the beginning of something new. In loop quantum gravity, for instance, singularities don't exist. Instead, matter rebounds, birthing new regions of space-time. Information could survive this cosmic bounce, re-emerging in a baby universe or a parallel dimension. It's as if every black hole stitches a new thread into the multiverse's fabric, weaving lost data into realities we'll never see. So what does this mean for the universe's edges? If information can escape black holes, whether via holograms, wormholes, or rebirth, it implies the cosmos has mechanisms to preserve data even in the most extreme conditions. That's a hopeful thought, that nothing, not even the abyss of a singularity, can erase the universe's memory completely. But until we crack this paradox, one thing's certain: the boundaries of black holes and the edges of reality are far stranger than we ever dreamed. Rising from the heart of our galaxy like two colossal chimneys of pure energy, the Fermi bubbles are among the Milky Way's most enigmatic structures. These towering lobes of gamma radiation stretch 25,000 light-years above and below the galactic plane, a quarter of the way to intergalactic space, glowing with the fury of 1,000,000 suns. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, they've sparked a cosmic detective story with one burning question: what cataclysm could blast such titanic formations into existence, and what do they reveal about the hidden forces shaping our galaxy's edges? One leading theory points to our galaxy's supermassive black hole, Sagittarius A star, as the culprit. Imagine it feasting on an enormous cloud of gas or a wayward star 6 million years ago, belching out jets of high-energy particles that punch through the Milky Way's gas layers like a cosmic blowtorch. The remnants of that ancient outburst might be what we see today, ghostly imprints of a violent past, slowly fading into the darkness. Supporting this idea are the bubble's sharp, well-defined edges, suggesting a rapid, explosive event rather than slow, stellar winds. It's as if the galaxy itself bears the scars of a long-forgotten temper tantrum from its central beast. But not all astronomers are convinced. Alternative explanations suggest these bubbles could be the cumulative work of countless supernova stellar explosions, or even collisions between dark matter particles annihilating at the galaxy's core. There's also the puzzling fact that the bubbles emit not just gamma rays but X-rays and microwave radiation too, a layered energy signature that defies simple explanations. Why do these emissions line up so neatly along the galactic axis? And why are there faint, tendril-like structures weaving through the bubbles, as if tracing invisible magnetic highways through space? Then there's the boundary mystery. The Fermi bubbles don't just stop abruptly, their edges interact with the Milky Way's halo of hot gas, creating shock waves and turbulence that ripple through the interstellar medium. Some researchers argue these interactions might be funneling energy and matter toward the galaxy's outer reaches, effectively feeding the cosmic web beyond. Others speculate the bubbles could act as shields, deflecting high-energy cosmic rays that might otherwise spiral inward toward star-forming regions. The most tantalizing possibility: these structures might not be unique. If other galaxies harbor similar invisible giants, it could redefine our understanding of galactic ecosystems. Imagine every major galaxy as a living entity, periodically exhaling colossal bursts of energy that shape their surroundings in ways we're only beginning to detect. The Fermi bubbles aren't just relics, they could be a glimpse into an ongoing cycle of destruction and rebirth, written in light we've barely learned to read. For now, these gamma-ray specters remain a puzzle wrapped in an enigma. Whether fossils of a black hole's fury or evidence of something even stranger, they remind us that even our own galactic home still holds secrets towering above everything we think we know. You might think the Milky Way is an island in the vast cosmic ocean, drifting alone through the darkness, But zoom out far enough and a breathtaking truth emerges. Our galaxy is just one leaf in a sprawling cosmic forest called the Laniakea supercluster. This structure is so immense it defies comprehension, a gravitational tapestry woven from 100,000 galaxies, stretching over 520 million light-years. To grasp its scale, imagine the Milky Way as a single grain of sand. On that scale, Laniakea would be the size of a football stadium. Yet for all its grandeur, this supercluster might just be the first clue to something even larger lurking beyond our cosmic horizon. The discovery of Laniakea, which means immense heaven in Hawaiian, rewrote our place in the universe. Before 2014, astronomers mapped galaxies in terms of simple clusters and groups. But by tracking the subtle flows of galaxies drifting through space like leaves on a river, a team led by Brent Tully uncovered a hidden pattern. Nearly every galaxy in our neighborhood is being pulled toward a gravitational anchor near the Great Attractor region. This isn't random motion, it's the signature of an entire supercluster, with galaxies flowing along invisible filaments of dark matter toward shared cosmic watersheds. Picture a mountain range where galaxies slide down the slopes into valleys of shared gravity, each tributary feeding into Laniakea's vast basin. But here's where it gets strange. Superclusters like Laniakea aren't neat, isolated structures. Their edges blur into neighboring superclusters, forming an even larger cosmic web. Some researchers argue these connections hint at something more profound, that superclusters themselves might be nodes in a gargantuan hierarchy we're only beginning to trace. Think of it like discovering that what you thought was a single tree is actually part of an endless forest, and that forest might extend farther than our telescopes can see. The implications shake the foundations of cosmology. If structures larger than superclusters exist, they challenge the cosmological principle, the idea that on large scales, the universe is uniform. Some models suggest these megastructures could be remnants of quantum fluctuations from the Big Bang, frozen into the fabric of space-time. Others propose they're evidence of exotic physics, like dark energy interacting with dark matter in ways we haven't yet imagined. Perhaps most intriguing is Laniakea's fate. Unlike bound structures such as galaxy clusters, superclusters are destined to be torn apart by the universe's expansion. Over billions of years, dark energy will stretch these cosmic threads until they snap, scattering galaxies into the void like beads from a broken necklace. Even now, Laniakea's outer edges are being pulled away by forces stronger than gravity itself. So what does our place in this vast web reveal? That the universe isn't just a collection of stars and galaxies, it's a dynamic, evolving network with currents and continents we're only beginning to chart. And if superclusters are just the first layer of this cosmic onion, who knows what other structures lie waiting at the edge of the map? Picture the universe as a vast, uncharted labyrinth, but what if its true shape isn't an endless expanse, but something far stranger? The question of whether space is finite but unbounded isn't just theoretical gymnastics, it's a cosmic detective story with clues hidden in the very fabric of reality. Imagine floating in a spaceship, traveling in what you think is a straight line, only to eventually return to your starting point without ever hitting a wall or edge. That's the tantalizing possibility of a universe with non-trivial topology, a cosmos that folds back on itself like a cosmic Möbius strip. Take the donut universe hypothesis. Mathematically known as a 3 torus, this shape would mean space has a finite volume but no boundaries. Sail far enough in one direction, and you'd loop back around like a video game character exiting one side of the screen only to reappear on the opposite edge. The implications are staggering. If true, light from distant galaxies could wrap around the universe multiple times, creating ghostly duplicates in the sky, like seeing the same mountain range reflected in a hall of mirrors. Astronomers have actually searched for these repeating patterns in the cosmic microwave background, hunting for matching circles that would betray the universe's hidden geometry. So far, no luck, but the hunt isn't over. Then there's the dodecahedral model, where space forms a 12-sided die curved in on itself. In this scenario, the universe's finite size would create optical illusions on a galactic scale. A single galaxy might appear in multiple directions, its light taking different paths through the folded fabric of space-time. The eerie part, these doppelganger galaxies wouldn't just look identical, they'd be the same object glimpsed from different angles through the cosmic origami. But how could such a structure form? One theory points to quantum fluctuations in the infant universe. As space expanded during inflation, microscopic wrinkles in the primordial energy field might have been stretched to cosmic proportions, locking in a twisted topology that persists today. Others suggest collisions between bubble universes in the multiverse could have left behind topological scars, like fingerprints pressed into the dough of reality. The real challenge is testing these ideas. A finite universe would leave subtle fingerprints in the cosmic microwave background, specific patterns of temperature fluctuations that resemble a hall of mirrors. Some researchers claim to have spotted hints of these in the Planck satellite's data, but the signals remain controversial. Others propose that gravitational wave astronomy could reveal the universe's shape, as ripples in space-time might behave differently when traveling through a folded cosmos. What's at stake isn't just abstract geometry. If the universe is finite, it means there's an upper limit to how far we can see, not because light hasn't had time to reach us, but because space itself loops back. It would also rewrite the cosmic origin story, suggesting that the Big Bang didn't create infinite space, but rather unfurled a finite structure like a blooming flower. And lurking beneath all this is a profound question. If we're inside a cosmic donut, what or who might be outside it? The universe's topology isn't just about shapes. It's about the very nature of existence, whether we're floating in an endless sea or sailing on a vast, closed ocean where every horizon eventually leads home. Until we crack this puzzle, we're like ants crawling on the surface of a balloon, unaware that every straight line we walk is secretly a curve. At the very boundaries of the known universe, where galaxies fade into darkness and even light seems to stretch into oblivion, space-time itself might not behave as we expect. Instead of the smooth, predictable fabric Einstein described, the edge of reality could be a seething, turbulent froth, a quantum foam where the laws of physics dissolve into chaos. Picture the surface of a boiling cauldron, but instead of bubbles, you're looking at tiny, fleeting distortions where space and time twist and fracture on scales a billion trillion times smaller than an atom. This isn't just theoretical speculation. Some of the most cutting-edge theories in physics suggest that at these unimaginably tiny scales, the very concepts of here and now lose all meaning, replaced by a churning sea of uncertainty. The idea of quantum foam emerged from attempts to reconcile general relativity with quantum mechanics, two pillars of modern physics that stubbornly refuse to align. In relativity, space-time is a continuous stage, unbroken and predictable. But in the quantum world, everything is quantized, jerky, and probabilistic. When you push these theories to their limits, like at the edge of the universe or near the birth of the Big Bang, they clash violently, suggesting space-time itself might be pixelated, flickering in and out of existence like static on a screen. Some models propose that in this foam, microscopic black holes and wormholes could blink into being for fractions of a second before vanishing again, their fleeting existence warping the fabric of reality in ways we can barely imagine. What does this mean for the edge of the universe? If space-time breaks down into quantum foam there, it could create a boundary where traditional physics simply stops working. Light traveling through this froth might flicker or scatter unpredictably, as if the cosmos itself has a built-in haze at its outer limits. Some theorists even suggest that these quantum fluctuations could act like cosmic mirages, distorting our view of anything beyond the observable universe. Imagine trying to peer through a frosted glass window that's constantly vibrating. You'd catch glimpses of shapes, but never a clear picture. the wildest implication. Quantum foam might not just be a feature of the universe's edge, it could be woven into the fabric of space-time everywhere, just too small for us to detect. If that's true, then the smooth, predictable space we experience in our daily lives is an illusion, a sort of cosmic averaging out of trillions of microscopic ripples. It's like looking at a sandy beach from a distance. The grains blur into a smooth surface, but up close, it's all chaos and motion. For now, quantum foam remains a tantalizing idea just beyond our ability to test directly. But experiments like gravitational wave detectors and particle colliders are inching closer to probing these scales indirectly. Every time we push the boundaries of observation, we're not just exploring the edges of the cosmos, we're peering into the froth at the very foundations of reality itself. And that's where the most profound mysteries are waiting to be uncovered. Imagine the universe as a cosmic projector screen, where every star, planet, and particle is just a flickering image, a two-dimensional illusion masking a deeper reality. This is the essence of the holographic principle, one of the most radical ideas in modern physics. It suggests that all the information defining our three-dimensional reality, every event, every law of physics, might actually be encoded on a distant, two-dimensional surface at the very edge of the cosmos. Think of it like a movie. The immersive experience you see is just light projected from flat film. In this case, the film is the boundary of the universe itself. The roots of this idea trace back to black holes. When physicists like Stephen Hawking showed that black holes slowly evaporate, they faced a paradox. What happens to the information swallowed by these gravitational monsters? Quantum mechanics insists information can't be destroyed, yet black holes seem to erase it completely. The solution: maybe the information isn't lost, it's smeared across the black hole's event horizon like ink on a stretched rubber sheet. This holographic behavior hinted at something astonishing. The three-dimensional world inside the black hole might be described entirely by interactions on its two-dimensional surface. Now scale this up to the entire universe. If a black hole's interior can be encoded on its boundary, could our cosmos work the same way? Proponents of the holographic principle argue, yes, that every particle collision in a lab, every supernova explosion in deep space, even your thoughts right now, could be shadows of processes playing out on a faraway surface we'll never see. It's as if reality is a grandiose cosmic game of Pong, where the real action happens at the edges, and we're just watching the projection. But how could this possibly work? The mathematics behind it involves string theory and a concept called the ad-s/CFT correspondence, which suggests a perfect duality between a higher dimensional space and its lower dimensional boundary. Picture a room filled with smoke. The swirling patterns in the air seem complex, but they're entirely determined by the heat sources at the walls. Similarly, our universe's richness might emerge from simpler rules written on its outermost shell. The implications are staggering. If true, the holographic principle would mean that space itself isn't fundamental. It's an illusion woven from interconnected bits of information. Time, gravity, even causality might just be emergent properties of this cosmic code. Some researchers go further, speculating that if we could read the universe's boundary, we might find everything past, present, and future encoded there like lines in a cosmic script. Yet for all its elegance, the holographic principle remains fiercely debated. Critics point out that our universe doesn't perfectly match the idealized models where holography works cleanly. Others argue that without empirical evidence, it's more philosophy than physics. But upcoming experiments like precise measurements of quantum entanglement or subtle anomalies in cosmic rays might one day test this mind-bending idea. Whether the holographic principle holds or not, it represents a profound shift in how we view reality's fabric. The universe might not be what it seems, not a vast, empty arena, but a shimmering surface of information with every galaxy, every atom, just a fleeting reflection dancing at the edge of existence. Every second, trillions of ghostly particles pass straight through your body and the entire Earth without a single collision. These are cosmic neutrinos, the universe's most elusive travelers, and they've been streaming through space since the first second after the Big Bang. While we've detected neutrinos from the Sun and supernova, an even more ancient sea of these particles permeates everything, the cosmic neutrino background. This faint whisper from the dawn of time could hold startling clues about the universe's edges, if only we could catch enough of them. Unlike the cosmic microwave background, which shows us the universe at 380,000 years old, the neutrino background comes from just 1 second after creation, a time when the cosmos was a seething plasma too dense for light to travel. These primordial neutrinos carry an unobstructed view of the universe's most violent infancy, frozen in time like insects in amber. The challenge, they're absurdly difficult to detect. With no electric charge and nearly no mass, neutrinos interact so weakly with matter that a solid lead block would need to be light years thick to stop one. Why does this matter for the universe's edges? Neutrinos' indifference to obstacles means they could carry information from regions beyond our cosmic horizon, places whose light will never reach us due to the universe's expansion. Imagine them as cosmic postcards from territories we can't otherwise see. Some theories suggest subtle patterns in their energies might reveal gravitational waves from the Big Bang itself, or even the imprint of other universes brushing against ours in the earliest moments of creation. The hunt for these ghostly messengers is pushing technology to its limits. Projects like the upcoming Ptolemy experiment aim to trap relic neutrinos on graphene sheets chilled to near absolute zero, watching for the infinitesimal vibrations they cause. Others propose using Antarctica's ice as a detector, monitoring for the rare blue glow when a neutrino smashes into an atom. But the real magic lies in what we might uncover. If the neutrino background shows unexpected variations, it could hint at exotic physics, perhaps evidence that our universe collided with another in its first moments, or that space-time has hidden dimensions curling at the edges of perception. These particles might even carry traces of dark matter interactions from the cosmic dawn, offering clues to that other great mystery. For now, the cosmic neutrino background remains just beyond our grasp, a shadowy archive waiting to be decoded. But if we can learn to read its faint signals, we might discover that the universe's edges aren't empty at all. They're teeming with ghosts, and they're telling us a story 13.8 billion years in the making. The universe isn't just a scattering of galaxies, it's a delicate, intricate tapestry woven from threads of dark matter and gas, stretching billions of light years into the void. This is the cosmic web, the largest structure in existence, and its outermost tendrils might hold the keys to understanding how everything in the cosmos fits together. Picture it like a spider's silk on a dew-covered morning, glistening with galaxies where the strands intersect. But between those brilliant knots of stars lies something even more intriguing. Vast, almost empty corridors where matter is so sparse, it challenges our very definition of empty. These filaments, the highways of the cosmic web, aren't just passive scaffolds. They're dynamic rivers of gas and dark matter, funneling material toward galaxy clusters with a gravitational pull so immense, it shapes the fate of entire galactic neighborhoods. Simulations show these filaments should be teeming with faint, diffuse galaxies and intergalactic gas, but when we train our telescopes on these regions, we find ghostly voids where matter is mysteriously scarce. It's like walking through a forest and discovering stretches where trees simply refuse to grow despite fertile soil. So where did everything go? One theory points to cosmic feedback, the explosive energy of supernova and supermassive black holes blasting matter out of these filaments, leaving behind near-vacuum expanses. Imagine a galactic wind so powerful it sweeps entire regions clean, pushing gas into the depths of intergalactic space. Another idea suggests these voids might be relics of the early universe, regions where quantum fluctuations during the Big Bang left behind underdense patches that never fully filled in. If true, these empty stretches could be cosmic fossils, preserving the imprint of the universe's first trillionth of a second. But the real enigma lies in the gas we can't see. Observations reveal that the spaces between filaments glow faintly in X-rays, hinting at clouds of million-degree plasma too hot to form stars but too sparse to detect directly. This warm-hot intergalactic medium, or WHIM, could be the universe's missing matter hidden in plain sight, woven into the web's threads like invisible embroidery. The problem, it's so diffuse that spotting it requires staring at distant quasars for clues, watching how their light dims as it passes through these elusive gas clouds. Then there's the dark matter factor. The cosmic web's architecture is sculpted primarily by dark matter's gravity, meaning these filaments should be dense with it. Yet some regions appear suspiciously empty even of dark matter, defying simulations. Could it be clumping in ways we don't understand, or is there something else, an undiscovered force or particle, altering its distribution at the universe's edges? Some theorists speculate these ghostly voids might be evidence of dark matter interacting with itself, annihilating or decaying over cosmic time, the most mind-bending possibility. These gaps might not be empty at all. Quantum field theory suggests that even a perfect vacuum teems with virtual particles flickering in and out of existence. Could the cosmic web's voids be seething with quantum energy, a froth of potential matter and antimatter waiting for the right conditions to emerge? If so, the universe's emptiest places might someday birth entirely new structures, rewriting the cosmic web story all over again. What's clear is this: the cosmic web isn't just the backdrop of the universe. It's the loom on which reality is woven, and its fringes, those shadowy, half-empty stretches, might be where the next great cosmological revelations are hiding. Because in the gaps between everything we see, the universe whispers its oldest secrets. What if everything we know about reality is just half of the story? The mirror universe theory dares to suggest that beyond the edges of our observable cosmos, there might exist a parallel reality where the fundamental rules are flipped. A strange reflection where left becomes right, matter becomes antimatter, and time itself might flow backward. This isn't just science fiction. Serious theoretical physics explores how such a mirror cosmos could emerge from the same Big Bang that birthed our universe, forever yoked to ours by invisible threads woven into the fabric of space-time. Take the Hubble neutron, for example. In our world, it decays into a proton, an electron, and a neutrino in about 15 minutes. But in the 1960s, physicists speculated that some neutrons might instead decay into mirror particles, ghostly counterparts invisible to our detectors. If true, these fleeting transformations could be the first whispers of a hidden reality brushing against ours. The idea gained traction when astronomers noticed galaxies spinning faster than visible matter could explain. Could the missing gravitational pull come from mirror matter clusters, overlapping our universe like a shadowy twin? The most compelling hint might come from the cosmic microwave background. Strange asymmetries in its temperature map, like the infamous axis of evil, could be the gravitational fingerprints of a mirror universe tugging at ours from beyond the horizon. Picture two soap bubbles pressed together. The point where they meet would warp each bubble's surface. If our universe shares such a boundary with its mirror counterpart, the distortions might be etched into the oldest light we can see. Then there's the neutrino enigma. These particles oscillate between flavors in ways that occasionally defy predictions. Some theorists propose that what we're seeing isn't just random quantum behavior, it's neutrinos briefly tunneling into a mirror dimension before snapping back into ours. It's as if these cosmic messengers are slipping through a hidden doorway we can't yet open. But the wildest implication, a mirror universe could explain one of physics' greatest unsolved mysteries: why our cosmos is dominated by matter instead of antimatter. The Big Bang should have created equal amounts of both, leading to mutual annihilation, unless somewhere beyond our view, a mirror antimatter universe exists balancing the scales. In this scenario, the asymmetry we see isn't a flaw but a clue. Our universe's matter surplus might be the cosmic equivalent of seeing only one side of a coin. Of course, skeptics argue there's no direct evidence yet, but upcoming experiments like the upgraded LHC and next-generation neutrino detectors might finally catch matter flickering into its mirror state. Others are searching for mirror photons' dark light that could permeate our world, undetectable except through subtle gravitational nudges. The true allure of the mirror universe isn't just its strangeness. It's the possibility that the edges of reality aren't in points at all, they're gateways. A place where the familiar and the alien dance in perfect symmetry, waiting for us to recognize the reflection staring back. At the universe's farthest, loneliest edges, where galaxies thin to nothing and time stretches into near eternity, an unsettling thought experiment lingers. What if a single, solitary consciousness flickered into existence completely alone, with no past, no world, no stars? This is the Boltzmann brain paradox, a cosmic riddle that forces us to question not just the nature of reality, but whether our own thoughts and memories are even real. The paradox gets its name from 19th-century physicist Ludwig Boltzmann, who grappled with how order emerges from chaos. His work suggested that in an infinite universe, even the most improbable events must happen eventually, given enough time. A group of atoms could randomly arrange themselves into a fully formed brain, complete with false memories of a life it never lived. Not just once, but countless times over. In fact, in an eternally expanding cosmos, Boltzmann brains should statistically outnumber real, biologically evolved minds like ours by an unimaginable margin. So why does the universe appear so orderly? And how do we know we're not just fleeting aberrations, momentary flashes of self-awareness in an otherwise mindless void? Here's where the paradox twists the knife. If Boltzmann brains are more likely than real brains, then the odds say you are probably one of them, a consciousness conjured from chaos, doomed to dissolve as quickly as it formed. Every memory, every sensation, even the screen you're reading this on, could be an illusion generated by random quantum fluctuations. It's the ultimate solipsistic nightmare, a universe where nothing is real and every thought is just noise in the cosmic static. But physicists haven't taken this lying down. Some argue the paradox exposes flaws in our assumptions about infinity. If the universe isn't eternal, if it has a finite timeline or a finite volume, then Boltzmann brains become vanishingly unlikely. Others propose that the laws of physics might inherently prevent such aberrations, like an unseen hand tipping the scales toward order. And then there's the multiverse angle. In a sea of infinite universes, perhaps we're simply in one where the conditions for real, stable minds are favored, while the Boltzmann brains languish in unrealized branches of reality. Yet the most profound implication isn't about cosmology, it's about perception. The Boltzmann brain paradox forces us to confront how little we truly know about consciousness itself. If a randomly assembled brain can perfectly mimic lived experience, what does that say about the nature of existence? Are we more than the sum of our atoms? Or is identity itself just a fragile pattern in the chaos? For now, the paradox remains unresolved, a ghost at the edge of physics, whispering doubts into the foundations of reality. But whether it's a flaw in our models or a genuine feature of the cosmos, one thing's certain: the universe's loneliest corners might be hiding the most unsettling truths of all. The universe's final act isn't written in stone, it's written in the invisible tug of war between dark energy's relentless push and gravity's stubborn pull. Will the cosmos keep stretching forever into an icy, silent void, or will it eventually collapse back into a fiery singularity? Or could there be a third option, something so bizarre it rewrites the rules of cosmic destiny? The answer might lie in the very edges of reality, where the fate of everything hangs in the balance. First, consider the heat-death scenario, the slow, quiet unraveling of everything. As dark energy accelerates the universe's expansion, galaxies beyond our local group will eventually vanish over the cosmic horizon, their light stretched beyond detection. Star formation will cease as gas clouds are pulled too far apart to collapse. Black holes, the last sentinels of structure, will evaporate via Hawking radiation over trillions of years until even atoms themselves decay into radiation. The universe becomes a thin, cold soup of particles so distant they'll never interact again. Time loses all meaning because nothing changes, just an eternal, featureless equilibrium. It's the ultimate fade to black, but maybe the universe has other plans. If dark energy weakens over time, gravity could regain control, reversing the expansion in a dramatic big crunch. Galaxies would rush toward each other, their light blue shifting as space contracts. Temperatures soar until atoms are ripped apart, then quarks and gluons dissolve into a primordial plasma. The cosmos collapses back into a singularity, a mirror of the Big Bang, perhaps birthing a new universe in an endless cycle. Some theories even suggest this could explain the fine-tuning of our universe's constants. Each cycle resets the rules slightly until life-permitting conditions emerge by chance. Then there's the wild card, vacuum decay. Lurking in the fabric of reality could be a lower energy state, a true vacuum, hidden beneath our current false one. If a quantum fluctuation triggers this phase transition anywhere in the cosmos, it would unleash a bubble of destruction expanding at light speed. Inside, the laws of physics would rewrite themselves instantly. Chemistry, nuclear forces, even the nature of matter could change. One moment, stars and planets exist. The next, they're erased by a wall of new physics racing across the universe. The scariest part, it could already be happening somewhere beyond our observable horizon, and we'd never see it coming. But the strangest possibility, the universe might not have a single fate at all. Brain cosmology suggests our cosmos is a membrane floating in higher dimensional space, occasionally colliding with others. These collisions could reset expansion or create localized regions of contraction within an eternally inflating multiverse. Picture a cosmic ocean where waves of creation and destruction rise and fall independently. Some areas heat death while others crunch or rip apart. The truth is, the universe's edge isn't just a place, it's a ticking clock. And depending on forces we barely understand, that clock could count down to silence, collapse, or something beyond our imagination. Every observation of distant supernova, every measurement of the cosmic microwave background brings us closer to knowing which path we're on. But until then, the universe keeps its final secret, not in the darkness between stars, but in the invisible push and pull that will one day decide everything. Black holes dominate our cosmic nightmares, regions of space where gravity is so strong, not even light can escape. But what if the universe has a cosmic exit sign to match its one-way street? Enter white holes, the theoretical opposite of black holes, where nothing can enter and everything is violently expelled. Imagine a black hole running in reverse. Instead of pulling matter in, a white hole would spit it out at speeds approaching light, like a cosmic geyser erupting with the energy of 1,000 supernova. While no white hole has ever been observed, their potential existence forces us to reconsider the most extreme edges of physics, and whether the universe might hide these explosive portals at its farthest boundaries. The math behind white holes emerges straight from Einstein's equations of general relativity. Just as black holes are solutions to these equations with an inescapable event horizon, white holes appear as valid, if bizarre, alternatives. Some theorists suggest they could be the other end of black holes, connected via wormholes in a cosmic recycling system. Picture a black hole devouring matter in one corner of the universe, only for a white hole to vomit it out somewhere else, perhaps even in another time or dimension. It's a tantalizing idea, offering a potential escape from the crushing oblivion of singularities. Yet white holes come with a glaring problem. They violate the second law of thermodynamics, which states entropy, a measure of disorder, must always increase. A white hole's explosive output would require energy to concentrate spontaneously, like a shattered vase reassembling itself midair. To reconcile this, some physicists propose white holes could only exist in the immediate aftermath of the Big Bang, when the universe's extreme conditions might have allowed such violations. Others speculate they're black holes from the future, somehow flipped inside out by quantum effects we don't yet understand, the most radical theory. White holes might not be objects at all, but events. In loop quantum gravity, a black hole's collapse could rebound at the smallest possible scale, triggering a white hole explosion billions of years later. This would mean every black hole in our universe might one day transform into a white hole, turning death into rebirth on a cosmic timescale. The catch: these reborn white holes would be microscopic, erupting with the energy of their former selves, but too small to detect unless one happened to go off right next door. Then there's the cosmic boundary angle. If white holes exist, they might not be scattered randomly but clustered at the universe's edges, places where space-time itself frays into something new. Imagine the Big Bang as the ultimate white hole, an eruption of matter and energy from an unknowable elsewhere. Could smaller versions of this primal explosion still linger at the fringes of reality, marking gateways to other realms? Some models of the multiverse suggest white holes could be puncture wounds in our universe's fabric, where higher dimensional space leaks through. The challenge, of course, is evidence. White holes would emit intense radiation, but distinguishing them from gamma-ray bursts or supernova is nearly impossible with current tech. Still, astronomers have scoured the skies for anomalies, outbursts with no visible source or energy patterns that defy known physics. One candidate, the bizarre object GRB 060614, flared with gamma rays for nearly a minute before vanishing, leaving no trace of a host galaxy or remnant. Could it have been a white hole's dying gasp? What makes white holes so compelling isn't just their strangeness, it's what they represent. If real, they'd prove the universe has emergency exits as well as traps, that destruction isn't always final, and that the cosmos might still hold mechanisms we've yet to dream of. Until then, they remain ghosts in the equations, reminding us that for every cosmic rule, there might be an exception waiting at the edge of everything. What if the universe's edge isn't a boundary at all but a glitch? The simulation argument, once relegated to late-night dorm room debates, has evolved into a startlingly plausible scientific hypothesis. At its core, the idea suggests our reality might be an artificial construct, an advanced civilization's digital playground. If true, the cosmic horizon where galaxies vanish into unreachability could be nothing more than a rendering limit, a buffer to conserve processing power. Picture a video game where distant objects fade into low-resolution textures to save memory. Now scale that up to universal proportions, and suddenly, the edges of existence take on a whole new meaning. This isn't just wild speculation. Physicists have outlined testable predictions for a simulated reality. One key clue could lurk in the fabric of space-time itself. At the tiniest scales, our universe appears pixelated, quantized into discrete chunks of energy and distance. If space-time isn't smooth but built from finite bits, it might betray the underlying code of a simulated cosmos. Some researchers even propose hunting for anomalies in high-energy particle collisions, evidence of computational shortcuts or rounding errors in the universe's physics engine. Imagine uncovering a cosmic equivalent of a software bug, a particle that briefly defies the laws of motion, or a gravitational wave with an unnatural frequency. But the simulation hypothesis isn't just about physics. It forces existential questions. Why would an advanced civilization build such a universe? Are we someone's ancestors resurrected in code to study our past? Or are we merely entertainment, a cosmic soap opera playing out for beings we'll never meet? Philosopher Nick Bostrom's seminal paper lays out the unsettling math. If civilizations tend to create simulations with conscious beings, the number of simulated minds would vastly outnumber biological ones. Statistically, you're more likely to be artificial than real. Critics counter that the argument is unfalsifiable, a modern-day version of "the dragon in my garage." Without direct evidence, it's metaphysics dressed as science, yet the debate persists because it mirrors a deeper truth. The universe often defies intuition. Quantum entanglement, dark energy, these weren't just unexpected discoveries, they shattered classical views of reality. If history's any guide, the next paradigm shift might be even stranger. The real twist, even if we're in a simulation, it changes nothing and everything. The stars still shine, the laws of physics still hold until they don't. The universe's edge might be a firewall, not of energy but of logic, and that's the haunting beauty of this idea. It turns the cosmos into a riddle not just about space and time, but about the nature of existence itself. Whether we're code or stardust, the question lingers: what lies beyond the rendered distance? As we've journeyed through these 30 cosmic mysteries, from the Great Attractor's invisible pull to the holographic echoes at the edge of reality, one truth becomes undeniable: the universe is far stranger than we ever imagined. Every answer we uncover seems to reveal 10 new questions, each more baffling than the last. Dark energy accelerates the cosmos into oblivion, while quantum foam churns beneath our feet. White holes lurk in equations, Boltzmann brains whisper existential doubts, and the simulation hypothesis turns reality itself into a cosmic guessing game. But here's the beautiful part: this isn't a story with an ending. It's an invitation to wonder, to question, to stare up at the night sky and feel that delicious shiver of the unknown. Maybe you're captivated by the eerie silence beyond our cosmic horizon, or the way galaxies stream toward some unseen destiny. Perhaps the idea of mirror universes or colliding dimensions sets your imagination ablaze. That's the magic of exploration. There's no single right mystery to chase. So what's next? The journey doesn't stop here. New telescopes peer deeper into the void, experiments probe the fabric of space-time, and theorists dream up worlds beyond our wildest fiction. And you're part of this adventure too. Hit subscribe to join us as we unravel the next cosmic enigma, because the universe isn't just a place, it's a conversation, one we're all having together. Drop your favorite mystery in the comments. Is it the phantom grip of dark flow, the haunting cold spot in the CMB, or something we haven't even discovered yet? The cosmos is waiting, and the next great revelation might just start with a spark of curiosity from you. Until then, keep looking up. The universe has plenty more secrets to share.